Welcome! In this session, we'll tackle the problem titled Minimum Operations to Make Array Equal. This is an interesting problem that tests your understanding of mathematical patterns and optimization techniques. Let's dive in. The problem begins with an integer n, which determines the size of an array ARR. The array is constructed using the formula ARR, I equals 2 asterisk I plus 1, where I ranges from 0 to n1. Essentially, this means that ARR consists of the first n odd numbers in ascending order. For instance, if n is 3, the array will be 1, 3, 5. Now, the task is to make all elements of this array equal using the minimum number of operations. An operation involves selecting two distinct indices I and j in the array, incrementing the value at index I by 1, and simultaneously decrementing the value at index j by 1. The result of these operations must be an array where all elements are the same, and the goal is to determine the minimum number of such operations required. The input is a single integer n with constraints 1 equals n equals 10⁻4, and the output is an integer representing the minimum number of operations needed to achieve this goal. To illustrate the problem, let's look at an example where n equals 3. In this case, the array ARR is 1, 3, 5. The target value for all elements is the median of the array, which is 3. To achieve this, we can perform the following operations. First, we increment the first element and decrement the last element, resulting in the array 2, 3, 4. Then, we increment the first element and decrement the last element again, yielding 3, 3, 3. At this point, all elements are equal, and it took a total of 2 operations. This demonstrates that the minimum number of operations required for n equals 3 is 2. Now consider another example where n equals 6. The array ARR is 1, 3, 5, 7, 9, 11, and the target value for all elements is the median, which is 6. To make all elements equal to 6, we pair the elements symmetrically around the median. For the pair 1, 11, it takes 5 operations to bring both values to 6. For the pair 3, 9, it takes 3 operations. Finally, for the pair 5, 7, it takes 1 operation. Adding these together, the total number of operations is 5 plus 3 plus 1 equals 9. Thus, the minimum number of operations required when n equals 6 is 9. If we look at the case where n equals 1, the array consists of a single element, 1. Since there is only one element in the array, it is already equal, and no operations are needed. Therefore, the output in this case is 0. This demonstrates that when the array has a length of 1, the result is always 0, as no changes are necessary. There are several important observations about this problem. First, the array is always sorted and contains the first n odd numbers, 1, 3, 5, 2 asterisk n1. The optimal target value for all elements is the median of the array, as it minimizes the total absolute difference. When n is odd, the median is a single value, while for even n, the two middle values are equal, making the median well-defined. The number of operations can be calculated efficiently using a formula based on the structure of the array, rather than manually simulating each operation. For edge cases, when n equals 1, no operations are required. For very large n, the solution must be efficient to handle the array size. Finally, the difference in behavior between even and odd lengths is naturally accounted for by the formula-based approach, ensuring correctness in all cases. To approach this problem, let's first restate the key details. We are given an array ARR where each element is defined as ARR, I equals 2 asterisk I plus 1, meaning the array consists of the first n odd numbers, 1, 3, 5, 2 asterisk n1. The goal is to make all elements equal using the minimum number of operations, where an operation involves incrementing one element by 1 and decrementing another by 1. Now, the first key observation is that to minimize the total cost, all elements should be moved to the median value of the array. This is based on the mathematical property of absolute differences. Additionally, because the array is symmetric, the median can be easily determined, it's n if n is odd, or n1 if n is even. Finally, the problem can be reduced to calculating the sum of differences between the median and the elements in the smaller half of the array, as these are the elements that need to be incremented to reach the median. One possible approach to solving this problem is through brute force simulation. The intuition here is to directly simulate the process by repeatedly incrementing smaller elements and decrementing larger elements until all values converge to the median. To do this, you would start with the array ARR equals 1, 3, 5, 2 n 1, identify the median value, and then perform the increment and decrement operations on the appropriate elements of the array. While this approach is straightforward, it is computationally expensive. Since we need to repeatedly adjust the values of the array, the time complexity is n squared, which becomes inefficient as n grows larger. Additionally, it has a space complexity of n. Due to these inefficiencies, this approach is not suitable for large values of n, making it impractical despite being easy to implement. Instead of simulating the operations, we can use a mathematical approach to optimize the solution. The key insight here is to leverage the symmetry of the array and focus on the arithmetic differences between the smaller half of the array and the median. Specifically, the elements smaller than the median need to be increment, while the larger elements need to be decrement. For the smaller half of the array, which consists of 1, 3, and 2, if n is even, or 1, 3, and 1, if n is odd, we can calculate the total number of operations required by summing the differences between each element and the median. Using the formula for the sum of an arithmetic series, this can be computed in constant time, giving a time complexity of 1 and a space complexity of 1. This approach is not only efficient but also elegant, as it avoids unnecessary iterations and directly leverages the mathematical properties of the array. The chosen strategy for this problem is the mathematical summation approach due to its efficiency and simplicity. The core idea is that the problem reduces to summing the differences between the median and the smaller half of the array. This eliminates the need for simulation and ensures that the solution runs in constant time. Comparing the two approaches, brute force simulation is easy to understand and implement but becomes computationally expensive for large n due to its quadratic time complexity. On the other hand, the mathematical summation approach is optimal and leverages the inherent structure and symmetry of the array to achieve a highly scalable solution. By focusing on the arithmetic properties of the array, we minimize computation and ensure the solution remains efficient even for large input sizes. To solve the problem, our goal is to determine the minimum number of operations required to make all elements in the array equal. The array, ARR, is composed of the first n odd numbers, starting from 1. For instance, if n equals 5, the array would be 1, 3, 5, 7, 9. An important observation here is that to minimize the total operations, we should aim to make all elements equal to the median of the array. This is because the median minimizes the sum of absolute differences, which is precisely the cost function we're trying to optimize. For an odd-sized array, the median is the middle element, while for an even-sized array, we can choose either of the two middle elements since the array is symmetric. To find the median, we can simply select the value at index n //2 since the array is already sorted. Now that we understand the importance of the median, let's move forward and break this process down step by step. For example, consider the array 1, 3, 5, 7, 9. The median here is 5. If the array were 1, 3, 5, 7, the median could be either 3 or 5, and both would yield the same result due to the symmetry of the array. Once we know the median, the next step is to calculate the total number of operations required. This involves summing up the absolute differences between each element in the array and the median. Mathematically, we calculate this as total underscore operations equals sum, abs, x median, for x in ARR. This formula gives us the minimum number of operations needed to make all elements equal. Finally, the result of this calculation is returned as the output. The key insight here is that the median minimizes the cost function, which is the sum of absolute differences, and this property is what makes our approach both optimal and efficient. Additionally, the symmetry of the array of odd numbers simplifies the process further, as it ensures that the array is already sorted. The algorithm operates with a time complexity of n. This is because generating the array takes linear time, and computing the sum of absolute differences also takes linear time. Together, this gives us an overall complexity of n. Let's take a closer look at the data structures we use. First, there's the array ARR, which stores the first n odd numbers and is generated using the formula 2 *i plus 1. Next, we have the median, an integer that holds the middle value of the sorted array, serving as the target value for all elements. Finally, we use an accumulator variable to compute the total underscore operations, which sums up the absolute differences efficiently. To see how this works in practice, let's go through a specific example. If n equals 5, the array generated is 1, 3, 5, 7, 9. The median of this array is the value at index 5//2, which is ARR, 2, equal to 5. With the median identified, we can proceed to calculate the total number of operations. Using the array 1, 3, 5, 7, 9, and the median 5, we calculate the total operations as follows: 1 5 plus 3 5 plus 5 5 plus 7 5 plus 9 5. This simplifies to 4 plus 2 plus 0 plus 2 plus 4, resulting in a total of 12 operations. Therefore, the minimum operations required to make all elements equal is 12. Let's also consider some edge cases. For the smallest input, where n equals 1, the array is 1, and the median is also 1. In this case, no operations are needed, so the total is 0. For an even n, such as n equals 4, the array is 1, 3, 5, 7. The median can be either 3 or 5, and the total operations calculate to 10 in either case. Finally, for a large value of n, the algorithm remains efficient because of its linear complexity, ensuring that it scales well even for large inputs. This makes the approach practical and robust for all valid inputs. This code solves LeetCode problem number 1551, minimum operations to make array equal. The goal is to find the minimum number of operations needed to make all elements in an array equal. The array consists of the first n odd numbers. 1. The function min operations takes a single parameter n, representing the size of the array. 2. The array is implicitly 1, 3, 5, 2 n 1. The optimal value for all elements to converge to is the median of the array. If n is odd, the median is the middle value, equal to n. If n is even, the median is the average of the two middle values, which simplifies to n plus 1. 3. The variable operations keeps track of the total number of operations required. We only need to calculate the adjustments for the first half of the array since the adjustments are symmetric. For a loop iterates through the first n//2 elements, representing the smaller half of the array. For each element at index I, the difference between the target value, median, and the current value, 2*i plus 1, is added to operations. 5. Finally, the total number of operations is returned. This approach is efficient, running in O(n) time complexity, as it processes only half of the array. It avoids the need to modify the array directly, making it both space efficient and computationally fast. This is the Java implementation of LeetCode problem number 1551, minimum operations to make array equal. The logic mirrors the Python implementation, calculating the total operations required to equalize the array. The median value is determined based on the length of the array, and the sum of differences for the smaller half of the array is computed in a loop. Key differences include type declarations for variables and the use of Java's loop syntax. To solve this problem, we need to calculate the minimum number of operations required to make all elements in the array equal. The array is defined as the first n odd numbers, ranging from 1 to 2*n 1. Since we can only increment or decrement an element by 1 in each operation, the most efficient way to equalize the array is to have all elements converge to the median. For example, when n equals 3, the array is 1, 3, 5, and its median is 3. The smaller half of the array consists of elements less than the median, which is 1 in this case. To equalize, we calculate the difference between the median and each element in the smaller half. For I equals 0, the difference is 3 1 equals 2, and we add this to our total operations. Since the smaller half contains only one element, the total number of operations required to make the array 1, 3, 5 equal is 2. Now, let's analyze the case where n equals 4. The array becomes 1, 3, 5, 7. When n is even, the target value is a virtual median, which is n plus 1 equals 5. The smaller half of the array, consisting of elements less than the target value, is 1, 3. For each element in this smaller half, we compute the difference from the median and add it to our operations counter. For I equals 0, the difference is 5 1 equals 4, so we add 4 to the operations. For I equals 1, the difference is 5, 3 equals 2, and we add 2 more. Summing these differences, the total number of operations needed to equalize the array 1, 3, 5, 7 is 4 plus 2 equals 6. Next, let's consider the case where n equals 5. The array is 1, 3, 5, 7, 9, and since n is odd, the median is the central element, which is 5. The smaller half of the array, containing elements less than the median, is 1, 3. To determine the total operations, we calculate the difference between the median and each element in the smaller half. For I equals 0, the difference is 5, 1 equals 4, and we add 4 to our total. For I equals 1, the difference is 5, 3 equals 2, and we add 2 more. Adding these results, the total operations to make the array 1, 3, 5, 7, 9 equal is 4 plus 2 equals 6. To summarize the key insights from this problem, the array always converges to its median value when equalized. For odd-sized arrays, the median is the middle element, while for even-sized arrays, it is a virtual median calculated as n plus 1. Importantly, we only need to consider the first half of the array, as the second half mirrors the operations applied to the smaller half. The difference for each element in the smaller half is calculated using the formula median, 2 * I plus 1, where I represents the index. This approach ensures efficiency, as the algorithm requires only a single pass through the first half of the array, achieving a time complexity of O(n). The time complexity of this solution is determined by analyzing each step of the algorithm. First, the median calculation is performed using a simple conditional check. This operation is constant in time, or O(1), since it doesn't depend on the size of the input. Next, we have a loop that iterates over the first half of the array. This loop runs n divided by 2 times, where n is the size of the input. Within each iteration, we compute the difference between the median and the current element, which is also a constant time operation. Additionally, we sum these differences into a variable, which again takes O(1) per iteration. Since the loop executes n divided by 2 times, the total time for this step is linear, or O(n). Finally, the return statement, which simply outputs the accumulated result, is another constant time operation, O(1). When these steps are combined, the overall time complexity of the solution becomes O(1) plus O(n) plus O(1), which simplifies to O(n). Combining the time complexity analysis, we see that the dominant term is O(n) due to the loop, so the overall time complexity is linear. Now let's consider space complexity. The space usage in this solution is minimal. The input variable, n, occupies constant space, or O(1). Temporary variables such as the median, the operations accumulator, and the loop variable also require only constant space. Importantly, this solution does not use any additional data structures or recursion, so no extra memory is allocated beyond these variables. As a result, the total space complexity is constant, or O(1). This efficiency highlights the elegance of the approach in both time and space utilization. To better appreciate the efficiency of the solution, let's compare it to a brute force approach. In a naive implementation, we might simulate the entire process of making the array equal by repeatedly applying operations until all elements converge. This would involve multiple passes through the array, leading to a time complexity of O(n squared). In contrast, the optimized solution avoids redundant computation by focusing directly on the smaller half of the array and using a mathematical formula to sum the required operations. This approach reduces the time complexity to O(n), making it significantly more efficient. The linear time complexity comes from the fact that the loop runs n divided by 2 times, with each iteration performing constant time operations. Additionally, since no extra data structures are used, the space complexity remains constant at O(1). This mathematical precision ensures that the algorithm is both time and space efficient. Finally, let's consider the best, average, and worst cases for this algorithm. In all scenarios, the time and space complexities remain the same. The time complexity is O(n), as this is determined solely by the size of the input, n, and not by the specific values within the array. Similarly, the space complexity is always O(1), as the algorithm only uses a fixed amount of memory regardless of the input size. Since the algorithm is deterministic and doesn't involve any conditional branches that could alter its performance, its efficiency remains consistent across all cases. This consistency makes it a robust and predictable solution for the problem. Let's start by addressing some common mistakes that can occur when solving this problem. First, misunderstanding the problem statement is a frequent issue. Remember that the array ARR is predefined as ARR I equals 2 asterisk I plus 1. Some users mistakenly treat it as an arbitrary array, which leads to incorrect approaches. Always confirm the constraints and definitions given in the problem before diving into a solution. Another common pitfall is overcomplicating the solution. For instance, while dynamic programming or other complex algorithms may seem appealing, this problem actually has a much simpler mathematical solution. It's important to analyze the problem for patterns before jumping into code. Additionally, handling odd and even cases incorrectly is another frequent mistake. The calculation of the median can differ slightly depending on whether the array size is odd or even, so getting this wrong often leads to incorrect results. Misjudging the median's role is another critical error. Many assume that values like the mean or the first element minimize operations, but it's the median that minimizes the sum of absolute differences. Lastly, watch out for off-by-one errors in indexing. Since the array uses zero-based indexing, miscalculating indices when finding the median or iterating through the array can result in edge case failures. Double-checking these nuances helps avoid unnecessary mistakes. Now let's discuss some valuable interview insights related to this problem. The key concept here revolves around minimizing the sum of absolute differences. The optimal strategy is to align all elements to the median, which is a fundamental property in mathematics. Interviewers often focus on efficiency, so while sorting the array to find the median in O and log n is acceptable, they may prefer a faster O n approach using the quick select algorithm. If you're familiar with quick select, it's an excellent way to demonstrate your understanding of algorithms and computational efficiency. Another important aspect is explaining edge cases. Be prepared to discuss how your solution handles scenarios like an array with just one element, or when the array is already uniform. This shows that you've thoroughly considered all possible inputs. Additionally, interviewers may ask you to justify why the median is the optimal choice for minimizing absolute differences. Being able to mathematically derive and explain this property, possibly with examples, can leave a strong impression during the interview. Let's look at some related problems that can help you build a deeper understanding of similar concepts. One direct variation is LeetCode 462, which also involves minimizing the sum of absolute differences. It's a great way to practice applying the median-based approach in different contexts. Another problem to explore is LeetCode 121, which, while not directly related, helps improve your ability to recognize patterns and optimize solutions efficiently. Then there's LeetCode 453, which is a similar problem but focuses on using addition to make all elements equal, rather than minimizing absolute differences. Lastly, LeetCode 216, which involves finding combinations that meet specific constraints, is excellent for sharpening your mathematical reasoning and constraint handling skills. Working through these problems can help you develop a broader toolkit for tackling variations of this challenge. Finally, let's explore some alternative approaches to solving the problem. One straightforward method is the sorting-based median calculation. Here, you sort the array and pick the middle element as the median, then calculate the sum of absolute differences. This approach is easy to implement, but it has a time complexity of O n log n due to the sorting step, which may not be ideal for very large arrays. A more efficient method is using the quick select algorithm to find the median in O n time on average. Quick select is faster but requires careful implementation and can be tricky to debug. For those looking for an even more efficient solution, a mathematical insight can be applied for this specific problem. Since the array structure is predefined as ARR I equals 2 asterisk I plus 1, you can directly calculate the result using patterns or formulas. This achieves O1 time complexity but is limited to structured arrays like this one and cannot be generalized. Each of these methods has its trade-offs, so choose the one that best fits the problem constraints and the context of your solution. That wraps up our solution to minimum operations to make array equal. We explored a mathematical approach that optimizes both time and space complexity. Remember, analyzing patterns can turn complex problems into elegant solutions. Thanks for watching, and stay tuned for more coding challenges. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!